Can y'all hear me okay?
Yeah.
Okay, good. All right, so let's get started. Just some announcements. Just again, if you have lab questions, please ask them on the discussion board. And some people have been asking, which is great, because I know that some of the questions that are asked, I'm sure other students have questions on it. So you have a homework due tomorrow night, and I can use time after class to answer questions on the homework. You have a Biot-Savart law worksheet due next Wednesday. That was a little bit more challenging than the one you just turned in, because as usual, when you're doing problems when you're calculating a field using calculus, it's always a little bit of a challenge for you to learn how to do them. So on this worksheet, really it's all in the setup, and I set up the problem basically to illustrate to you this is how you set up the problem, this is how you approach it. Okay, because really it's a calculation, and you're just going through a process to solve it. And by going through step-by-step process, it'll allow you to figure out where you will get stuck. Now, the first problem, the integral is doable because it's like the one I did in class the other day. Second one, you're going to have to do in Wolfram unless you want to challenge yourself. Okay? And the second one, the setup is a little bit more challenging, but that's okay. I mean, the idea is the process is the same thing. Even though the geometry is different, you're still following the same process. And that's part of the goal of the worksheet, is that even though the geometry is different, you're doing the same thing. And so you might get lost in maybe some of the details, but you're still going to do it the same way as the first problem. Okay, so I'm sure that I'll probably get questions next week on this worksheet. Okay, and I'll be ready for your questions on it. And then again, May 4th is your fourth exam. What I want to do today is I want to clarify some things on the Hall effect. Although I'm going to still claim I'm still not going to go through all details. I just don't have time. I want to say a few more things about forces on wires in magnetic fields, and then I want to do Ampere's law. Okay, and I should be able to get everything done today, and then on Tuesday I will be able to start chapter 31, which to me is probably the most interesting part of the course. Okay. Just in case, you guys can hear me okay, right?
Yeah.
Okay, all right.
Yeah.
Okay, so let's start by going back and quickly clarifying some things on the Hall effect. If you recall, and I'm not going to draw that detailed picture that I did last time, you have a conductor, a thin conductor. I guess I'll draw it in 3D. Carrying current to the right, and there's a magnetic field perpendicular to this plane. And what happens, and this is the height of this thing is d. What happens is if you put a voltmeter, a sensitive enough voltmeter, across the top and the bottom end, you will measure a voltage called delta V sub H. And we showed that this is equal to the drift velocity times the strength of the field times this distance. And one of the questions was why should this conductor be thin? Because when you read about it, it says, if you want to really observe the Hall effect, why should it be thin? And it's really hard to see it from this equation. However, remember the expression for the current using our model for current. Current is N times Q times the drift velocity times the area. So what's the area? What area am I talking about in this particular case?
D times the thickness.
Area.
Yeah, it's going to be the thickness times D, right?
Mhm.
Right? It's the area perpendicular to the current. So A is basically D times T. So let me write that down. Now, if you solve this for V sub T, that's V sub D. And then you substitute it in here, you will see that it's going to depend on, this thing will depend on 1 over T. The T will be in the denominator. So that means that if you make T smaller, this gets bigger. And that's where that comes from. Okay? And I kind of had omitted, I wasn't planning on discussing that, so I didn't really look at that when I was preparing for the course, for the lecture. So that's my bad. But yeah, so you want it to be thin because, if you solve this for the drift velocity, you'll get a T in this denominator. Okay? And you can do a lot of other, you can go through a lot of other details regarding the Hall voltage, but I'm going to leave it at that for now. Now the other question, there was another question regarding, can you make this large enough so that the electrons just do a complete circle? And we got to be careful because when you ask that question, you are assuming that the electrons are not colliding with anything else. Okay, so if you want to go into more details, yeah, T is this thickness. Okay. If you want to go in more details to better understand this, or at least a better model, you have to use the Drude model, the model for current, and realize that as the electrons, yeah, the electrons are going to be deflected upward in this particular, let me use purple. The electrons are going to be deflected upward, but as they get deflected upward, they're going to collide with other, either electrons or with other, with protons. So if you take into account those collisions, what you'll get is the vertical component of the drift velocity will be upward. And the charge will separate. And so you'll end up with an excess of negative charge here and an excess of positive charge here. So in regards to your question, Ravtej, that's really what you need to do. And one could go and read through the theory, but you end up getting two, you have to set up two equations. I don't have time to go through that, but you can actually go through and solve it. But even that is still a simple model.
Mhm.
Okay.
Yeah.
So yeah, you can do that. But again, I've been trying to keep my descriptions simple. But yeah, you can do that. And if you take a course in solid state physics, which you usually don't do that till junior level or graduate school, then you will go through this in more details. You'll first add the Drude model for current, and then you will, on top of that, add quantum mechanics to it. But even when you add quantum mechanics, you got to use a statistical model involving quantum mechanics so that because otherwise the problem is too difficult. It's a difficult problem if you want to know it at a high level of detail. So what you're looking at is you're looking at collective properties, right?
Mm-hmm.
It's very difficult to look at it one by one. Okay. So that's an upshot, my clarification on the Hall effect. All right. So now let's go back and talk about forces on wires. So the other day,
Can I ask a question about this?
Yeah.
So the Q stands for the total charge on the.
The Q stands for the charge of each charge carrier. So if it's a conductor, they're going to be electrons. This is the magnitude of the charge of each electron.
Okay, and then the N is the number of electrons?
The number of electrons per unit volume.
Oh, okay.
Right. This came from when we went through chapter 27. This is where when did we derive this expression in chapter 27, where we said N is the number of charges per unit volume. Q is the charge of each charge carrier. V sub D is the drift velocity. And A is the cross-sectional area. And then, of course, you can take I over A while we're at it, I guess. That's the current density. So a lot of times we can rewrite, and again, I'm not going to go through it, we can write some of these equations in terms of the current density. Okay. If you want to be very general, and I'm not doing that here.
Okay, thanks.
Okay. Yeah, and I was looking through, through textbook. It's really not until you get, and I have my solid state physics book on campus. I don't have it here, but it's a graduate level book. They will go into this topic in a lot more detail. So that's how complicated this topic can be if you start looking at it in more details. Okay. So if you're wondering why we avoid some of these details, because they're just difficult. We talked about the force between two current carrying wires, I1 and I2. And we calculated the force per unit length on each of the wires, and we got the following expression. Where D is the separation between the wires. And what do we use? Well, the equation we used was number one, this one. And number two, the force, the magnetic field due to a wire, an infinite wire, which we obtained from the BO sub R law. Okay, we obtained this from the BO sub R law. And one of the things we discovered is if the currents are parallel, the two wires attract each other. If the current in one of the wires is reversed, guess what happens?
Repels.
They will repel. And again, you can justify that for yourself using the right-hand rule. Okay? So go back, watch the video where I did this problem in detail, and then just reverse the current one of the wires, and you'll see right away that they'll repel. So it'll go this way. It's consistent with Newton's third law. What if, instead of having this nice geometry, we have, let's see, let's take three wires. And the wires come out of the board. Let's pretend they're infinitely long. Let's pretend that these wires are infinitely long, but they form an equilateral triangle. And guess what I'm going to ask? I want to know the force on this one. Let's call the currents, let's say all the currents are the same, just to make life easy for ourselves. Let's say they're all I. I want to find the force on this top one due to these bottom two. And in fact, let me do something different. Because maybe the color coding might be a little bit better. Can you see that okay?
Yeah.
Okay. I want to know the force on this top object. What do I do first?
Find the force due to the bottom one, and then the bottom left one, and then the bottom right one.
Yeah, I want to do something before that.
Direction.
So what do you call that? What do you mean by finding the directions?
Like the bottom right one and the top one, they attract each other.
Okay, so
And
what am I drawing then?
Vectors.
Coordinate system?
I'm drawing a free
We
body
need a
diagram,
coordinate
right?
system.
Oh, okay. Yeah.
Right? Okay, again, I'm going to say this again. This will probably be the last time I can say it in this course. When you think of force, what's the first thing that should come to your mind?
Drawing a diagram?
Yeah, you got to draw the free body diagram, okay? So first thing that comes to your mind is you were saying the right, those of you folks were saying the right things. I just wasn't hearing the word free body diagram because I want that to be etched in your mind when you think of forces, okay? Because that gives you the best opportunity to be able to solve this problem successfully. So yeah, you do have to look at the force between these two. Okay, so these two wires are carrying currents in the opposite direction. This one's carrying current into the board. This one's carrying current out of the board. So what's going to happen to this one relative to this one?
It's going to repel.
Repel. So it's going to want to go, and it's going to repel along the line joining the two wires, right? Let me draw a line joining the two wires. So the repulsion is going to be along the line joining the two wires. So that orange vector represents the force between these two. And maybe what I'll do is the following. I will number these 1, 2, and 3. And then, so the force at the top here, this one is going to be the force on wire 3 due to 1. So what are these two going to do?
Attract.
They're going to attract each other along the line joining them. This is the force on 3 due to 2. Since the currents are the same, and since this we said that this is an equilateral triangle, what can you say about the resultant force?
To the right.
Yeah, it's going to be, so the resultant force will be, you're right, to the right. Will be that way. Why? Because I'm going to, and some of you guys, folks said it, I got to find the force between these two, right? I got to find the magnitude of the force between these two. It's given by this expression, right? Oh, the force per unit length. Right, I got to say the force per unit length, right? Because these are infinite wires. And I got to find the force per unit length between these two, and it's given by this expression. And all the i's are the same, and all the distances are the same. So the lengths of the vectors are the same. So this length and this length is the same. And so what you'll see is the y components will cancel, just leaving you an x component. Does that make sense?
Mm-hmm.
Hold on, I guess the question, why only? Oh, I circled one of the numbers, that was just my mistake. I'll circle all of them. Sorry about that, Aiden. Yeah, you're right. The x component of one of them will double. That's your final answer. So basically your final answer is going to be 2 times f sub x. That's it. So all I got to do, calculate this, find the x component, double it, I'm done. That was easy, right? But if you don't have symmetry, then what?
You need
You
to
have
add
to
all the
find-
forces.
Yeah, you gotta resolve the x components for this one, and the x components for this one, the y components for this one, the y components for this one. Add the x components together, add the y components together, use a Pythagorean theorem, and then the inverse tangent function, right?
Professor,
Yes.
I'm sorry, I kind of got a bit confused there. When you say it's of infinite length, are you talking about between the wires or like the way they extend in and out of the board?
They come out of the board, right?
Yeah,
Now, I'm not
that's
saying the triangle is infinitely big because then the force would be zero. But well, I got to be careful with that. But the wires are infinitely long, so the magnetic field due to each of these wires can be written as B equals mu naught I over 2 pi R. Okay?
yeah.
So because this equation is valid for wires that are infinitely long. So they got to come all the way out of the board. So I'm still using these two equations. The only thing that's different is I gotta exploit the vector nature of forces to be able to solve this. So and the reason why I bring this up is because when students get to this chapter, guess what they do with the forces? They add them like numbers. When we get to this chapter and we do force problems, students will calculate these two forces, and just add them like numbers, not like vectors. They forget that force is a vector. I don't care. I mean, it doesn't matter whether the force is due to magnetic fields, electric fields, gravitational fields. It's a vector. The math doesn't care. So you got to still use the techniques of vector addition. So, Michaela, you said what? I mean, with regards to...
I know, that's because you said, like, guess what they do? And I was like, what?
Oh, okay, sorry. Okay, are we okay with this then? Because you do have problems in the homework, and I don't want to go through an example just because you guys have added forces together in the past. And if you really want to remember how to do problems with forces, I have some videos on electric fields, how to do the electric field problems. All you got to do is change it to magnetic fields. That's it. Okay. The vector, you just exploit the vector nature of forces. All right, I want to do one more example. Actually, I want to say one more thing about this case. It is this system that's used to define the amp. Okay, you can actually use this system to define the amp. It's a device called the current balance. Because the forces, small forces can be measurable, like forces of 10 to the minus 7 newtons can be measurable. Okay, you can actually use this system to define the current, the ampere. Okay, so one more example is this. This has something in the worksheet, something from the worksheet, and something from what we just talked about in it. So let me draw the picture, and I want to leave this equation, these two equations up here. All right, so I have a wire carrying current I. That's supposed to be a straight wire, okay? And then I have below it a loop carrying current I also. It's a rectangular loop. I'm not doing a circular loop because that's much more difficult. And so it's carrying current like so. And this distance is D. This distance is D plus A. And I'm gonna define downward as positive just to make everything easier. Okay, when I do my calculations. I want to know the force on this loop. Let's pretend, so this is infinitely long. This is not. We'll just say its length is L. L by A. I want to know the force on this loop. And of course, using Newton's third law, I can find the force on that, on the wire, okay? So how do I approach this? This thing has 4 sides. And I'll put circles around the values. All right, it has 4 sides. How do I find the force on the entire loop? Well, you just did a worksheet. What did you do with the worksheet? You found the force on each segment, right? And then added them together. Isn't that what you guys did?
Mm-hmm.
Okay. So you can do the same thing here. But maybe, hold on a second. But maybe we can cancel some things out because of some symmetry.
Professor?
Yeah.
Would the vertical components, like the vertical lines, like segment 1 and 3, would those not contribute, or
Well,
would they?
Good question. Why would they not contribute?
Because looking at the 2 equations you have in the bottom, I think you derived that for the 2 wires that were parallel, but since segment 1 and 3 are perpendicular, the cosine of 90 would be 0. So I was thinking the force would be 0. Or
Well, we got to be careful because even though the wires are perpendicular, the magnetic field, I'm sorry, well, even though the cross product, if they're perpendicular, is maximized, right?
yeah.
Okay. But the magnetic field, use the right-hand rule, actually goes into the plate of the board, right? The magnetic field looks like this. And I got to be careful. I got to choose a different color. The magnetic field goes into the board everywhere in this plane. So anywhere along here is into the board. The only difference is that it gets weaker the further away you get from the wire because of this equation. So it's not 0 because of the fact that the cross product gives you 0, but it's 0 because these 2 currents are in opposite directions. Do you see that? The L switches sign here and here.
So in that the segment with the 1, it's going into the board, and for 3 it's going out of the board.
No, it's going into the board too.
Oh.
What's different, this direction is different.
Oh, okay.
Right? One's up, the other one's down. Right? They're 180 degrees out. And so that's going to cause the cancellation. Does that make sense?
Yeah.
Okay. And actually, I'm going to explicitly do one of the sides. Okay. I just want to. But okay, so they'll cancel. So these 2 will not, right? And in fact, the field's going to be the same value anywhere along this line. Isn't that true? Because the magnetic field depends on how far away you are from the wire. Anywhere along this line, you're the same distance from the wire. Isn't that true?
Yes.
And then same thing here. I don't want to keep drawing these blue things because otherwise it's going to obscure the rectangle. But this is further away than this. So the force on this piece is going to be smaller than the force on this piece. Isn't that true?
Mm-hmm.
Okay, furthermore, and we got rid of some of our purple arrows. Let me draw them in. These 2 are going to be attracted to each other. Isn't that true?
Mm-hmm.
And these 2 are going to be repelled. So basically, I can just use this equation twice to calculate the force on this guy and the force on this guy. So really, the total force is going to be, and I don't need the force per unit length because this is not infinitely long. The force is going to look like this. And I can factor things out, I guess. I forgot an L. And the force is downward. I'm sorry, the force is upward. Are we okay with that? So I solve for the magnitude of the force. That makes sense?
And then can we just directly write it as upwards?
Yeah, you can say that.
Okay.
Yeah, yeah. If you want to be really careful mathematical, then you would write it in terms of unit vectors. Okay. Depending on how you define your coordinate system. I'm going to define down as positive because when I do the integral, it's going to make my life easier. Because the next thing I'm going to do is I want to find the force on one of these. I want to find the force on this segment. I know that this one's going to cancel this one, but just for fun, I want to find the force on this one. This is your worksheet.
So we don't have to worry about the like each side of the wire loop, the force on each other. Like, do those do they not
this one on
affect
this
each other?
one?
Yeah.
Well, I'm asking for the force on the loop, correct?
Yeah.
So if I consider the force on each other, won't they cancel out?
Oh, okay.
Right?
Oh, right, because that's what we did on the last worksheet.
No,
Oh, wait, no, that was different.
Yeah, we didn't even consider that on the last worksheet. But since you brought it up, I mean, this is something you cover. Well, this is this is a detail I talk about when I teach 205. Those are internal forces, and internal forces cancel each other out.
Oh, right.
Right, because the force on this guy due to that one is upward. I mean, let's say is in one direction, and the force on this guy due to this guy is in an equal and opposite direction. If you add them together, you get 0. And you could do the two ones on the side too. So those are internal to the system, and forces that are internal to the system, they all cancel out.
Oh, okay. I was just curious.
Yeah. So in general, all internal forces acting on a system cancel out. So if you're going to make something move, you have to apply a force that's external to a system. All right. So I want to find the force on number 1. So I have to set up an integral. Why?
Field is varying.
I'm sorry?
The field
distance.
is varying.
Yeah, because it depends on distance, right? The force depends on distance. So I need to write dF is I dl cross B. And I'm going to say down is positive just to keep the math simple, because otherwise I got to deal with minus signs. And now I was confused myself. So if I'm going to say down is positive, actually no, let me not do that. I got to make sure I still have a right-handed coordinate system if I do that. Never mind about saying that. Let's just say down is negative like usual. This side's negative. Okay. So my dl is j dy. And B it's in the minus k hat direction. It's into the board. And, oops. not being careful. Okay, now what do I got to do next? When you did the worksheet, what did you do next?
Normally it's a determinant, right? But do we have to? Because we know that it's going to be in the I hat direction since the cross products are in the J and K.
Is it in the minus I hat direction?
Yeah.
Okay, so then this is going to be I'll put the minus sign out here. Does that look okay?
Yeah.
So that's the force on the little element of this wire. So now I want to integrate to get F. So let's be careful here. Is this a coordinate or a distance?
Coordinate.
It's a distance. Okay, this is actually a distance. It's the magnitude of the vector that points from here to here. Okay. So that means I got to write these as positive numbers. So I'm going to integrate from d to d plus a. And I'm going to get what do I get when I integrate that?
The same thing times a natural logarithm.
Okay? And then you would get something in the opposite direction on this side. And then it'd cancel. Because if you do this side, then this would be negative. And it would cancel, everything would cancel out. Okay, so that's why these two cancel. So there's another, just more practice on forces on wires in non-uniform field. Forces on wires in non-uniform field. So I can ask you another question. What's the torque on this loop?
There's no torque
Why?
because there is no force into or out of the board on the two, like on any component, on any side of the loop.
Well, let's use the definition of torque.
And they have the same line of action.
Okay, yeah, that's right. Okay.
Yeah.
Yeah, I was looking at that. Right. I'm looking from our definition. Mu is into the board, and B is into the board. They're parallel, so this cross product is 0. The magnetic field would have to have a component in the plane of the loop for this thing to experience the torque. Okay. All right. And then we can also ask about the potential energy would be minimized because the potential energy both of these are into the board, so the potential energy will be minimized.
Professor, could I ask a question on what's in the blue again on the right hand? I was wondering why they were being subtracted.
These two? Oh, over here and over here?
Yeah.
But the currents are in opposite direction, right?
Yeah.
So these two attract, these two repel.
Oh, okay.
Okay. Okay. All right. So now I want to talk about a fairly important topic. it does have limited applications. And I will tell you that I'm going to derive this the wrong way, but this is historically how it happened. Okay? I mean, what I'm going to be saying is not completely true. But this wasn't discovered till years later. So for many years, people saw that what we're going to derive to be correct. But there's something missing in my discussion. And we won't see that until we finish chapter 31. But anyway, we'll proceed down the wrong route. And there's a big subtlety in what I'm going to say. So suppose I have a long current carrying wire, okay? And let's see. The magnetic field wraps around this wire. The magnetic field wraps around. And this is always so hard for me to draw. Oh, that looks terrible. The magnetic field wraps around like so. Okay? At some distance away, right? This is some distance away from the wire. Suppose I choose an imaginary loop, and what I'm gonna say here is a lot of hand waving, because to actually derive this requires your knowledge of Stokes' theorem, which not everybody has. Okay, so I'm hand waving. Suppose I, just for fun, integrate the magnetic field around a loop, the same loop as this field line. Okay? Suppose I do that. Integrate around that loop, all the way around, closed loop. Well, my DL is going to be in this angular direction. You guys took 205 from Aviva. So what is the direction around the loop? The unit vector, what did you call it? When you took 205.
Is that R hat or?
Not the R hat, but the other one, right? Yeah, the theta hat. I'm gonna call it the phi hat because I'm using Greek letter phi. And so the DL is going to be R d phi hat. But the magnetic field is in the same direction. The magnetic field loops around like that. It's mu naught I over 2 pi R. Oops. Hold on a second. So what happens to this dot product between these two vectors that are parallel to each other?
Simply multiply the coefficients.
Yeah, I mean, if you do this, what is that equal to? It's the same thing as this. It's 1, right?
Yes.
Okay, so that's going to give you this. What do you end up with? So the integral of the magnetic field around a loop is equal to this. It really doesn't depend on the geometry. I chose a nice geometry because it works very simply. But if you want to do it in general, you have to use Stokes' theorem.
Professor,
Okay.
could I just clarify something really quick?
Yeah.
Is the DL, is that an infinitesimally small distance between the wire and, oh, okay.
And this is the R. Right, because you're integrating around a loop that's the same as this field line.
Wasn't the r hat direction? Oh no, the theta hat direction was the one that was perpendicular or like tangent to the circle, was it?
Yes.
Okay, yeah, I understand. Thank you.
Okay. So this is true in general. It's true in general that if you integrate the magnetic field around the closed loop, it's going to be equal to mu naught times I. And I got to write down I enclosed. What does that sound like?
Gauss's law.
Yeah, this is not Gauss's law for magnetic fields, but this is analogous to it because guess what? If I can pull the b out of the integral sign, I can calculate b, right? But the number of applications for it is, there's very few applications. We can use this to calculate. We can use this for calculating the magnetic field. But this is called Ampere's law. This is the third of Maxwell's equations. However, that's not entirely correct. This is correct as long as the magnetic field does not vary with time. Okay? Now, there's a subtlety here about that loop. And yeah, Michaela, we did use a dot product. Every once in a while, we're using the dot product. Even when we do the flux calculation, we're using a dot product. There is a subtlety because this integral is valid around any surface that the loop encloses. Whether the surface is the plane, the planar surface of that loop. So if I can draw a loop like this, and I integrate like this around the loop, that integral is true for any surface for which this current penetrates. Because this current is going to penetrate any loop that's enclosed by this. So even if I choose a surface like this wire is going to penetrate that loop. It's going to go in on one side and come out the other. So it's going to penetrate that surface. So it doesn't matter what kind of surface this loop encloses. It's true for anyone.
By surface, do you mean volume or do you mean area?
Area.
Okay.
And again, this goes back to the following, because we can always write I this way. And this is the surface we're talking about. Okay, so I can be written this way. The current density dotted with the normal to the surface, dot dA. So part of it is it comes from this, but the other part is it comes from Stokes' theorem, because we can work back from this and go back to Stokes' theorem, but I can't do that here. Okay, so that's an important thing. I mean, so if your current does this, then what? How much current is enclosed?
0.
0. Okay, that doesn't penetrate that surface.
Can you explain again what the blue shape is doing? Sorry, it just slipped.
The blue shape or the purple?
Oh, sorry, is that purple? Then I guess I'm just colorblind. Put the purple one.
What this thing is doing, it's not really doing anything. It's just that we're saying that the expression has to be true no matter what the surface. Why should it be particular about the surface that the loop encloses? The question, are Maxwell's equations just different versions of the other people's law, like Gauss's law? Gauss's law stays the same. So, Brandon, Gauss's law is the same. They call it Maxwell's equation. Actually, they should be called a Maxwell Heaviside equation because both of them were involved in this. Gauss's law for electric and magnetic fields don't change. That one does. That's the only one that changes. But it was Maxwell who discovered the problem with this thing. Okay. So in regards to your question regarding the surface, remember this is an imaginary loop we draw, just like we drew an imaginary surface for Gauss's law. But this must be true for any surface enclosed by the loop. Why would it be particular to a loop? And then this is part of a Calc 3 thing. Right, this is part of Stokes' theorem.
Is it because the magnetic field is continuous for all points in space that we say that it can do this?
Is it because the magnetic field is continuous?
Yeah, for all points in space, right? Because that's the justification you use for being able to integrate around the the boundary of a surface, is that the inside always cancels out.
Yeah, it is continuous. You're right. I haven't thought about it. It's been a while since I've looked at that level of detail.
Yeah, I've been reading through my Calc 3 notes recently just because it's popping up so much. I figured I'd look at it.
Yeah, I mean, it has to be continuous. You're right. That function has to be continuous. That's a good point. But I mean, remember that when you have a wire going through this loop, it doesn't matter what surface you attach to this loop, the current's gonna penetrate that surface. But you will see when we get to the next chapter, we're gonna get a case where we have a problem. Okay, we'll get to that. All right, we'll worry about that later. Okay, so that's important to understand that, I mean, this is where our problem is gonna come in. Okay. And by the way, it's also important that we understand that I is the integral of j dot dA, which you can put here. So we need to say a couple of things about Ampere's law. So if you have a loop of wire, okay, and let's say the current is coming out of the board. Okay, so you notice the magnetic field due to this loop of wire is in the same direction as, if I integrate in the same direction as the magnetic field, my integral is going to be positive. If I integrate against the direction of the magnetic field, my integral will be negative. Does that make sense? I'm just doing a sign convention thing. So if I integrate in the direction of the magnetic field created by the wire, this ends up being positive. Just a sign convention.
Hey, Professor, I'm sure that this has been answered or can be answered very simply, but didn't we say that magnetic field lines always need to start and end on a pole?
Well, all we said was they form closed loops. I didn't say I never said that they start or end on a pole, right? Because if I have a bar magnet, this is the north, this is the south. The magnetic field lines go like this. They all form closed loops. So inside, you're going to have something like this. We never draw what's inside the magnet.
Right. Okay.
Okay. Well, all I said was they just go from north to south. Okay. So,
Professor?
yeah.
So on that wire where we have that loop drawn of the magnetic field, can we define the north and south for that as well?
Well, if you put a compass, I mean, you can do it here, I guess. Right? So you would say this is the north, this is the south, over a small region.
Okay, so overall there is no north or south for it.
I don't know why that's important.
No, I was just asking.
Okay. Yeah. I mean, if I put a compass, the north pole of the compass would point that way, right?
Mm-hmm.
So this would be the south pole. You can define it over a region, right? But not over the whole loop. You can't do it over the whole loop because it closes upon itself.
Mm-hmm.
Okay. Okay. Let me advance my slide. So this is analogous to Gauss's law. The only thing different is you integrate around a closed loop, not a closed surface. The current I is the continuous current passing through any surface bounded by the closed path. And the problem is going to come in as to when we have a current that's not continuous. So what was your question again, Damien, about the surface? You're saying the magnetic field's got to be continuous, right?
Yeah.
Yeah, and that's a good point. But we're going to end up doing a problem where the current is not continuous. But we're going to end up forcing the magnetic field to be continuous. Actually, you brought up a good point, which I didn't think about. Maxwell's going to introduce another term that's going to make the magnetic field continuous. So yeah, that's a good observation, which I didn't really think about because I haven't looked at it at that level in a while. If you want to use Ampere's law to calculate magnetic fields, you need to have a high degree of symmetry, even higher than in Gauss's law. In order for you to use Ampere's law to calculate a magnetic field, the magnetic field has to be uniform over the loop. So the fact that the integral is not zero, that's true for any vector that has a rotation around a closed path. Any vector that circulates, any vector that curls. Curl is the operative term for you guys who are in Calc 3. Okay? It really tells us that the vector can rotate. Okay? So I want to do a couple of examples where I apply, let me check the time, where I apply Ampere's law to calculate magnetic fields. So I'm going to do it for a thick wire, not a thin wire, because this is the thin wire. The answer is obvious for a thin wire. Okay, I want to do a thick wire with a uniform current density. And I want to calculate the magnetic field everywhere inside the thick wire and outside of the thick wire. I'm going to add a video to your module. There's this person from Yale, his name is Shankar. He gives a fantastic He does basically he uses chalk and board, that's it. But he gives a fantastic discussion on this topic. And so much better than your book would do it. Okay, so you might want to watch that video. So I'll put it on Canvas. Okay, and it's captioned and everything. Okay. So let's say we have a thick wire. And the radius is capital R. And it's solid. I want to find the field out here and in here. So let's say that the current is directed towards the right. I want to use this expression to calculate the magnetic field for distances bigger than this value and distances smaller than this value. So here's where the problem comes in with the mu naught, calculating the magnetic field inside here. Let's just say for simplicity, the permeability of the material is mu naught. If I choose the right material, it would be some constant times mu naught, okay? Let's assume that the wire is not iron, it's not made out of iron. Anyway, iron wire would be extremely brittle, be useless for carrying current anyway. Okay. Using our knowledge of magnetic fields, what can you say about the direction of the magnetic field outside the wire? All right, I mean, if you're standing outside the wire looks like this. And the magnetic field circulates. Use the right-hand rule. Like that. So isn't it true that outside here, the magnetic field circulates like this, so that at the top it comes out of the board and at the bottom it goes into the board. Right? Are we okay with that? Mm-hmm. And it's going to have the same value anywhere around this loop. So if you look at it from the side, whatever distance you are from the wire, no matter where you are, if you rotate this thing, it's going to always look the same, right? So the magnetic field, at whatever distance you are from this wire, is going to have the same value because of rotational symmetry of this thing. So that means for any value r, the magnetic field will be the same. So then I'm going to use this expression, the integral of B dot dl. Okay. And it's going to be equal to mu naught times I enclosed. Since I'm integrating about dl, when the magnetic field has the same value anywhere around the loop, I can just take this out of the integral sign and integrate around dl. We're choosing B and dl to be in the same direction to make life easy for ourselves. Then what's dl?
Would it be the circumference?
Yeah.
Yeah.
Well, I enclosed just I. And so then B.
Professor, would it be a capital R or no?
No, because we're outside, right?
Oh yeah, okay.
Or actually, if we were on the surface, then it would be capital R. If we were on the surface, we would write capital R. So then B would end up being mu naught I over 2 pi r, as you would expect. Because we did this using Biot-Savart law. Now, what if we're inside? So let's do inside the wire. So now I'm going to choose a loop like this. Whatever current is enclosed in that loop, whatever current is penetrating the surface of that loop of wire is going to the right. We're still going to have the same symmetry as we had before. So for any distance, little r, from the center of the wire, the magnetic field is going to have the same value as I go. If all I have to do is rotate the wire, it looks exactly the same. Okay? So, I'm still going to set up this integral, the integral of b dot dl equal mu naught times I enclosed. And because b is going to be the same all the way around the loop, I can pull the b out, and then the loop is a circle, so I'm going to get, again, b times 2 pi r. So now the problem is, how much current is enclosed in this loop?
Do we have to do the I is equal to the integral of j dot n dA thing?
Yeah, so now that's equal to mu naught times the integral of j dot n dA. Now what's j? Well, j points to the right, and I'm going to choose my surface to be flat. So I'm going to choose the planar surface. And I'm going to choose n in the same direction as j. I'm going to choose n, and n is chosen by the direction I'm integrating, by the way. So it's that way. So that these two are parallel to each other. But what's the magnitude of j in this particular case? Well, since the current density is uniform, it's going to be the total current divided by pi r squared. I guess I should make this a capital A. Sorry.
Sorry, could you repeat what the n vector was?
It's the unit vector that's perpendicular to this surface. The surface I choose that encloses the wire. That's enclosed by the wire.
So it's
I'm gonna choose, my normal is chosen by the direction I integrate. Right hand rule, curl my fingers around the direction of integration, my thumb points to the right. Okay?
okay, so it's like the same direction as like what you have that r, that your radius pointed, that one arrow.
Well, this R is just a radius, so.
Oh yeah, but like I was just like using the arrow as like a reference.
Okay, so yeah, the thumb points like that. So that's the direction of n hat. It's in the same direction as j hat, or j.
Okay.
So then my element of area for a disk, because I'm integrating, I chose a disk, my dA, if you remember from before, is going to be 2 pi r dr. I made a mistake. You guys didn't catch it. It's a capital R. So pi cancels. Let's continue. I want to make sure you guys can see the board. I'm going to use black so it's let me know if it's hard to see.
Wait, shouldn't the like on the upper board, shouldn't that R be capital?
Up here?
That's on the outside.
Because if we're outside, we're at a distance bigger than R. Right? The radius, this is the radius of the circle.
Oh, I thought the inner
You're talking about this R?
Yeah.
That's this R.
Oh, okay.
That's the first part. The second part is down here.
Okay.
Okay, so now I have mu naught times I over R squared, and there's a 2, the integral of R dr. Oh, I have a problem here. What should I do?
Call it R prime.
I'm sorry? Should I call it R prime?
Yeah.
Okay. So when I integrate this, what do I get?
R squared over 2.
Okay. Oops. This 2 cancels with this 2, and I get mu naught I R squared over big R squared. Now what? Solve for B. Divide both sides by this, and I get B is mu naught I times R over 2 pi R squared. Now, when you're on the surface, little r is big R, guess what you get? Mu naught I over 2 pi R. Okay. So what the field looks like, if I were to make a graph, running out of space, looks like it's linear inside. And then when you get to the surface, it decreases as 1 over R. That's what a graph looks like. Now, what if the current density was not uniform? What if the current density was not uniform? Then what?
Do we have to integrate for it also?
Yeah, we couldn't pull stuff out. It'd be part of the integral, right?
Mm-hmm.
And you guys have done that before, right?
Yeah.
Okay. So you do have a homework problem where that's pretty much this problem where the density is not uniform. Same procedure, except that when you integrate this, nothing can be pulled out except the numbers, like number 2 or the numerical constants. Okay? All right. Let's do another example. The device I want to look at is a solenoid. The solenoid is a long current carrying wire that's wound in the form of a helix. And I'm going to use Ampere's law to calculate the magnetic field due to a solenoid. This is where that video from Yale, he does a fantastic job on this problem. So let's say I have a long wire wrapped around some tube. And the wires are very closely spaced together. Okay, that should be enough. I don't want to draw every single one. Actually, I should have drawn it down here, but that's okay. What can we say about the magnetic field? Let's say the current.
It should be in the same direction as the wire, right?
I'm sorry?
Should it be in the same direction as the tube it's wrapped around?
Yeah, in fact, in this particular case, if you look at, for each loop, the magnetic field wraps around, right, like this. And inside the wire, inside the tube, the total magnetic field will end up being that way. Each one of these is going to contribute to the total magnetic field inside the wire. The ones that are next to each other, anything in between here will get canceled out. And then you're going to get something way out here. So field lines should kind of wrap around. Remember, we'll wrap around all the way around like this. So we're going to assume, though, this is very long. We're going to assume that this is infinitely long. This is what imagine a long version of this. This is a solenoid. Okay, a long solenoid is one where L is much, much greater than the diameter. Okay? So imagine it's really long. And so this thing would have to loop way out there. It would have to go way to infinity and loop around to infinity. So what I want to do is calculate the magnetic field here and in here. Okay, so we know the field lines are going to loop like this, right? Going to loop like this, so. I should have used a different color, but. Suppose I choose a loop. In fact, let me do this. Let me just draw this one like so. And let me choose a loop that is rectangular. I was choosing the wrong color, sorry. I'm going to choose a rectangular loop to do this integral, if you guys don't mind. This field line essentially is going to be horizontal here, essentially in this region. Over the center of the tube, this is essentially going to be horizontal. Okay? I want to use this expression. How much current is enclosed through here? How much current penetrates that loop?
0.
0. So there's no current that goes through this. So for now, when I choose this loop, I must have this has to be true for this loop. So that says one of two things. Either the magnetic field is either 0 or it's uniform. Why do I say that? Well, if the magnetic field line points to the left, and I look around this loop, if I have a magnetic field line that points to the left around this loop, when I integrate around this guy and this guy, what do I get?
The same thing, but equal and opposite.
Well, actually, I get 0 for both because they're perpendicular to each other. The dot product is 0.
Oh,
Right? Now we'll go to these two. Now go ahead and say what you said before.
they're the same thing but equal and opposite.
Yeah, these two are equal but opposite. So number one, so B has to be uniform. They have to be equal but opposite for this to be 0. So either B is uniform or B is 0. No matter how long I make this, that in this direction, not including this thing. So as I go further and further out, I make this longer and longer and longer. So I keep this in the same location, but I just keep making this longer and longer and longer. That integral is 0, right? Because there's no current enclosed in the loop.
Right.
But if I go all the way to infinity, what's the field going to be at infinity?
0.
0. So what does that say then about the magnetic field? If
It
it's
has to
0,
be 0.
I'm sorry?
It has to be 0.
It has to be 0. So the magnetic field out here is 0. The magnetic field above is 0. Okay? So that's going to establish the fact that the magnetic field is there. Now, what you can also do is use some intuition saying, well, these things over here, they curl around and you get cancellation in between the wires, et cetera, et cetera. So you can use some physical arguments to show that it's 0. Okay? Or you can use this argument to say, oh, it's 0 out here. So out here it's 0, up here it's 0. But what about inside? What if I choose a loop like this again? What can they say? Suppose I choose that loop, just inside the solenoid. What can I say?
There is still no current, right?
Yes, there's no current, right?
Mm-hmm.
So what are the things I can say?
B
we've,
is uni-
we've established that there's got to be a field in here and it points to the right. So these two legs don't contribute. But what can I say about these two contributions to the integral?
They're equal and opposite. So.
You're going to say B is uniform, right?
Mm-hmm.
So that's going to establish the fact that B is uniform. So how am I going to get B? How about if I choose a loop like this? Now, each one of these wires is going into the board, so I should put now let's calculate this integral. Well, this guy and this guy will not contribute, right? Will this one contribute? No, because what's the field outside?
0.
0. So over the 3 legs, this integral is 0. So now the 4th leg, the magnetic field is constant over this length. And so the integral then over that 4th leg gives you just B times L.
Are there more efficient geometries than a solenoid?
I'm sorry, they're more efficient.
Geometries, like ones that produce a, because that one's like linear with how far it travels down the solenoid, right? Are there ones that do better than linear?
For a solenoid?
Or just for any geometry, like it doesn't need to be a solenoid.
There's a torus. I take the ends
Gotcha.
of the solenoid and bring them together and form a circle.
Oh, and that's why they're circles, the particle accelerators, right?
Those are the tokamaks, the ones that confine plasmas. They kind of have that shape. Particle accelerators are just generated from electric fields. I mean, there's different ones, but you're talking the donut-shaped ones are called the tokamaks. They're for plasma confinement. So let's continue with this. So how much current is enclosed?
None.
Well, there's this one, there's this one, there's this one, there's this one, there's this one.
Oh, so is it just like n time the amount of rings enclosed?
Yeah,
times-
whatever that number is, right? N times I. So the magnetic field is just mu naught times N over L times I. So what is this? This is the number of turns per unit length. So we write it this way. So N is just the number of turns per unit length. That's it. And that's the field to a solenoid. Now, I'll do the torus next time. I want to get a chance to actually get a torus. I forgot the torus. I forgot to get one from campus to get to see what it looks like. In the notes, and I'm not going to go through the problem. I have two problems that I've solved in the notes. Whoops. Hold on a second. And then I'll stop. I actually did the solenoid using the Biot-Savart law, which is fun. Okay, well, I did a finite solenoid and then I made it very long. So I actually have this problem solved in your notes, and I don't have a video on it, but you can actually read through the notes on this problem. This is actually a hard problem. And so I kind of went through in details how to calculate the magnetic field of the solenoid. So first I did one loop, and then I integrated over all the loops. Okay, so I have this completely solved, so you can take a look at it. So I do the solenoid, but here's the thing, I want to get to the graphs.
Wait, which problem are we talking about? The one that we just went over?
Yeah, but I did it with the Biot-Savart law. I have it in your notes, and I usually don't go over it in class, but you can read through it.
Yeah, we can't see your screen. I don't know if I'm the only one, but it just looks.
Oh, you can't see the screen? I'm sorry.
No, we cannot.
Oh, okay. So let me go back. Let me. Let me go back in the slides. Sorry, every time I change something, the display changes. So I solved, darn it, I gotta do it again. Okay. That's not what I want to do. It's gonna mess up again. Sorry. The software is very annoying. All right, you see it now, right?
Yeah.
Okay, good. So this is the problem I set up and I solved it. I did it for one loop. And then I integrated over all the loops. So it's completely worked out in your notes. If you want to go through a challenging problem for practice, this is a good one. Okay? But what I want to get to is the graphs. These graphs illustrate the magnetic field due to a solenoid. I did this in Excel. I did all kind of work with this a long time ago. But I plotted the magnetic field as a function of the distance of L over R, the length of the solenoid over the radius. Notice what happens when the length over radius ratio gets bigger. The magnetic field gets more uniform and more uniform as you're inside. And it drops off very quickly to 0. Okay. And that equation I derived shows that. I even have an equation, and I didn't put it in the notes, where I actually put multiple layers on the solenoid. That was a horrendous problem to solve. But anyway, this shows you the solenoid problem and what happens as the solenoid gets longer. And the equation approaches mu naught n times I. So when L over R is 500, the length over the radius is ratio is 500, you can almost think of it as an infinite solenoid. Look at how it drops off so fast. Okay. Then I also do another problem. I do this problem, which looks like the one I did in the notes, except this is out of the plane of the board. I'm calculating the magnetic field out of the plane of the board. So I'm not sure where that symbol came from. So this is worked out in gory details. Okay? So you might want to read through those. Because they would give you extra practice. Okay.
If you don't have anything to do, like at this immediate moment, could I ask you a question or two about the problem we just went over?
Yeah, just I'll say a couple more things. So.
Oh, okay, yeah, sure.
Just on Tuesday, I'll do the torus, and then I'll start chapter 31. The torus is quick, okay? And it kind of reviews the lecture. And I'll put up that lecture by the person from Yale, because I think it's great on Ampere's law. Go ahead and ask your questions.
So talking about the loop that's completely outside the first one we did, where we used the justification that, like, as you stretch out the bottom to infinity, the field is equal to 0 there.
Yeah.
We ended up saying that the field at the top part of that loop also has to be 0, and that's because, like, that comes from the fact that we know that the integral of b dotted with dl is going to be equal to 0, right?
Yes. Well, because we already established the field's uniform, right?
Right, or that it's 0.
Yeah. The integral is 0. Yeah, that's true.
Okay. And then the reason you chose a rectangle is because the field lines at the top and the bottom are approximately completely parallel to the top and the bottom of the loop, right?
Yeah, they're pretty much in a straight line, right?
Right.
So if they circulated, if the field lines made a full circle, if the field lines do a full circle, then you want to use something more circular, right?
Right, yeah, something with more curvature or whatever. Yeah.
You cannot use Ampere's law if you have, let's see, a loop of wire carrying current. All right, let's say you have a loop of wire carrying current like this. The magnetic field is much more complicated, so that you cannot use that expression. Okay, so let's say you want to find the magnetic field, at the center. You actually have to use the Biot-Savart law to do that.
I see.
Okay. Or you want to find the field anywhere inside here, you want to use the Biot-Savart law. Now the problem with the Biot-Savart law that happens when you're away from the center is the integral is not doable. Meaning, what I mean by that is, and I gotta be careful with my word choice. It doesn't mean it's not doable. It just means you don't have an analytical expression.
Right.
You have to do it numerically. However, there are power series. There are series expansions of the integrand that you can use, that you learn as an advanced undergraduate or in graduate school. And you have fun doing those kind of problems where you start now approximating what the field is from these expansions. And then you got to figure out how far do I carry out my expansion. That's fun stuff. But that's really where you're learning more about how to calculate something as opposed to learning really the physics.
Right.
So go ahead.
Oh, go ahead.
No, I was just going to say that Ampere's law using Ampere's law to calculate magnetic field is very limited. A lot more limited than Gauss's law.
Right. For the solenoid we were doing where it had the wires wrapped around it.
Yeah.
We were told in a problem that each one carries a current I, right?
The current through each loop is I guess. I mean, it's the same thing anywhere in the loop, right? I mean, anywhere in the wire. I'm not sure I understand your question, I guess.
No. You're saying it correct. I just meant like if the I in your little red final answer there is the current in each one of the wires.
That penetrates the surface of the loop.
Right. Yeah.
Yeah, it's just not just the single I, but it's every time you go through that surface, you got to count it.
Oh, so if you picked a loop and each wire went through it like 3 times, then you'd have to.
Yeah. So for the solenoid, you had. That goes through 5 times, that comes through 5 times, and you got to multiply by 5. That's why you multiply by n, right?
Right, but if one of the loops like was wrapped around twice, would you count the current from it twice?
Oh, you mean if there were 2 levels, 2 layers?
Yeah.
Yeah, you'd have to count it twice.
Okay.
And then I had to think about whether you can use Ampere's law if you have 2 layers. Because when you start adding a layer, you start losing symmetry. I've done the problem using Biot-Savart law where you have 1 layer and 2 layers, if I remember correctly. It's not a fun thing. That was a long time ago.
Professor?
Yeah.
On that same, like the solenoid that you have on the board, for that final rectangle, I thought that the current which was going into the board is also coming out of it from the bottom. So maybe I enclosed is 0 for that.
Well, did you do this for your loop or did you do this for your loop?
No, the same one that we did right now.
So you got a 0 for that?
No, I was just thinking that the current enters the loop and then exits as well.
How does it enter and exit? Because this is flat, right?
Yes.
I mean, it just penetrates in one direction.
Yeah, like the one, suppose like in the starting where we had a wire and we made a loop around the wire. Like I could see, okay, the current is enclosed in that loop.
So if
okay, never mind. I answered my own question. Okay.
Okay. All right.
Yeah.
Right. Obviously, and again, it's a bad picture. It goes in through the bottom and comes out the top, right?
Yeah. Mm-hmm.
That's fine, but but it penetrates the surface once.
Mm-hmm. Yeah.
Okay. So that's what you got to think of how many times it goes through the surface.
Mm-hmm.
So if there was another layer that wrapped into the plane or out of the plane of the board, then you start getting cancellation. But these all come out and go in the same direction.
Yeah. Mm-hmm. Okay.
Yeah, there's a lot of little subtleties in this, and the video I'm gonna put up. He goes through his subtleties. In fact, I think the video I'm going to show you is the second video on the topic. He actually does it twice. He comes back the next day and says, "Let me clarify some things," and he spends like I don't know, 45 minutes clarifying things. So,
Yeah, I think the reason I got confused for a second was because in Gauss's law we used a surface, and here it is like not a closed surface, but like a plane. So, yeah.
yeah, I mean, we always choose the flat surface because it's easier. But you can choose any surface. But then if you choose a different surface, the integral is horrendous.
Yeah.
Yeah, so you're trying to make life easy on yourself. So, and I will tell you where the problem comes in. When you have a capacitor and you try to apply Ampere's law when you have a capacitor. So here's your loop, and then here's a surface. Now you have a problem. And this is the issue that Maxwell tried to figure out. He came up with a solution. And that made the magnetic field continuous. So do you guys have questions on the homework or any other questions? Because I can use the time now to answer questions on the homework.
I was gonna ask where you were gonna post the Yale video. Are you just gonna inbox it to us? Like you're gonna email it to us?
I'm sorry, which video?
The Yale video.
Oh, I can do it after class.
Will you just email it to us and stuff?
Well, I'll just put it in the module. Is that okay?
Oh yeah, sure.
Yeah, there's a module for chapter 30. And when I update the module, there's a button on the bottom that says notify students that it was updated. So you should get a notification that it was updated.
Okay. Thank
Okay.
you.
Professor?
Would you mind going? Oh, go ahead, Ravtesh.
I was just thinking about that capacitor that you drew on the board. So is the problem due to the varying current in the wire, or is it something else as well?
Well, it is due to you do have a varying current. That's the problem.
Okay.
Yeah, you're going to get a time varying electric field.
Yeah.
So next lecture we're going to show that a time varying magnetic field generates an electric field, and then at the end of the chapter I'm going to discuss that a time varying electric field generates a magnetic field. And then Maxwell was able to put all his equations together and come up with some interesting. Basically, was able to predict light, the propagation of light. So, but it's all on this problem. He figured it out. So Einstein would always say, his accomplishments were huge, but we don't give him as much credit as we should. Although Heaviside has something to do with it too. Could I go number 11, part B? Sure. Let's take a look at number 11. By the way, just to tell you guys, number 9 is a 9D that doesn't have any correct answer.
After you do 11 part B, can you do number 14?
Okay. So this is that problem with the dipole. So you're standing on the Earth, and you know the compass measures the Earth's magnetic field in a plane tangent to the Earth at your location, right? Well, that's going to be hard. That would be hard for me to draw. But let's say you're on the Earth, right? And you have a compass. It's measuring the magnetic field locally in a plane tangent to the Earth, even though the Earth's magnetic field has a component this way. So the needle of a compass has a given magnetic moment, And the Earth's magnetic field is given, it has messed up units. So let's say, let's localize our picture. Let's say we're, this way is north. This is the horizontal, that's north. Okay. Okay, so the magnetic field points this way. You want to find the orientation that gives the minimum potential energy for the compass needle. So the potential energy for the compass needle is going to be, U is going to be minus mu dotted with B. It's going to be the magnitude of mu minus the magnitude of mu times the magnitude of B times the cosine of the angle between these two vectors. If mu and B are parallel, then this is minimized because of the minus sign. If mu and B are anti-parallel, cosine of 180, pointing this way, above the southern direction, then this is maximized. Is that okay, Aiden? And then how much work does it take to go from one orientation to the other? Just take the difference and mix max minus min. Right, the work done is the change in potential energy. Is that okay, Aiden?
Yeah, and the potential energy is just which equation exactly? It's
this one.
So that's the equation I was using. The problem is I think like maybe the units are like messing me up. And so the first one is like milliamps meters squared. So that's just that value times 10 to the negative 3.
Yes.
And then the next value is the 50, or the like the A hat.
Yeah, forget the A
microteslas?
hat. It's just microtesla.
Yeah, so it's just microtesla. So that's 10 to the negative 6.
Yeah, 59 times 10 to minus 6.
And then that's cosine of the theta. So I was like putting that value in a bunch, and it would continually give me the wrong answer. And so is there something else to this that I'm not getting, or?
It should be 2 times should just be that, the answer. Is their answer not correct? Hold on a second. Let me double check.
Yeah, let me try to.
Yeah, I got it to work.
I'm plugging in right now.
Okay.
That did work. Thank you.
Okay, good. Maybe it was punching something in on the calculator. So, Damien, you said 14?
Yeah, but before you answer that, is there a 2 there just because it takes twice the amount of energy to get it from like one configuration to the other, or one configuration to 0?
Yeah, because one's positive, you don't, oh, 1 to 0, but this is not from 1 to 0 though, right?
Right, but I'm saying 1 to 0 and then 0 to the maximum, or the opposite, right? That's 2 times.
Yeah, because
whatever.
they're equal but opposite, right? Well, so when you subtract,
Gotcha.
right? If you take 1 minus negative 1, for example, you get 2.
Right, right.
Yeah, yeah. Okay, let me try to erase this stuff. So you said I'm sorry, you said 14, right?
Yeah, the one with the cesium sputter negative ion source.
Okay. So you're trying to separate isotopes. So particles come out of an accelerator, and you're giving them some kinetic energy. So we talked about this the other day. So V is going to be 2q delta V over m square root. This is what comes out of the accelerator. And then this goes into a magnetic field, where now it's going to be forced to go in a circle. I should use a script V because this is confusing. So now, if we solve this for, what are we solving this for? You're solving for R, right? R is going to be what? mv over qb. But V, and I keep screwing that up. V is this expression, right? So this is the radius. So what are we given? We're given the radius of curvature for the lighter isotope is 21.9 centimeters. Well, that's my value. Okay. What is the separation of the two isotopes upon exiting the slit? So when these things go into a spectrometer, they travel a distance. The distance from here to here is 2r, right? Isn't that true?
Yeah.
Okay, so when they go from this point to this point, they travel distance 2r. So basically, the separation between the two particles is going to be 2 times r of the heavier one minus r of the lighter one. Okay? So if we want to write this in terms of the heavier one and the lighter one, what do we want to call the separation? Delta S? I don't know, whatever you want to call it. S for separation. This is going to be equal to 2 times m of the heavier one let's see, what can we do here? Is that okay so far?
Yeah, you just plug stuff in, right?
Yeah, well, all we know is, we know this number. We don't know this number, right?
Right.
We don't know Q delta V. So let's factor out some stuff. Let's factor out this thing. Let's factor out, let's see. Let me rewrite it. I'm going to put everything under the square root, if you guys don't mind. Okay, so this is the R for the heavier one, and this is R for the lighter one. What I'm going to do is factor this whole term out. So I'm going to factor this whole term out. So I'll get the following. So you know this number, right? This is the radius of the lighter particle. And you know the ratio of the masses, correct?
How did you factor out the mass of the lighter particle? Oh, I see. Sorry.
So you get a nice simple expression, don't you? After all that mess, you get a real simple expression. And that's it. So now you can just plug in the values. People who do mass spectroscopy, they have to know, they're familiar with these equations. Or they become familiar with these equations. I don't know if you do these in chemistry. Are we okay with that? I should choose hydrogen because then the separation is bigger. Because if I choose hydrogen, the heaviest isotope of hydrogen and the lightest isotope of hydrogen, the ratio is 3. That makes this a significant difference.
Okay, and then I had a question about. So I know that there's no correct answer for 9D, finding the magnetic torque, but would you mind going through that problem if it's doable?
9D? Well, basically, there should be a plus sign in one of them. It's going to be IA squared plus B squared times B over 2.
Yeah, I understand how to get the magnetic dipole moment, but for whatever reason, I would say the topic I'm struggling the most with in this section is the magnetic torque.
So we have let me draw this loop. Okay, it's a bad picture, sorry.
It's okay, mine's worse.
Mu points into the board, right? I'm sorry. Yeah, mu points into the board, right? If you use the right-hand rule.
Is that just because of the direction of the current?
Yeah.
Then yeah, I agree.
Okay. And so mu, the magnitude of mu, is going to be pi times I times this half area and this half area. What are the radii?
I think you wrote pi twice, right?
Oh, yeah. Okay, let's do it that way. Okay. And there's only one turn, if I remember correctly, yeah. And then B, where did B go?
B is the smaller radius.
Oh, okay. No, the magnetic field. Where's the magnetic field?
Oh, sorry.
Oh, the maximum magnetic torque. Okay, so let's say the magnetic field is in the plane. Like that, and it's uniform. Okay? So the torque is going to be mu. I'll get out of the way. Cross B. The magnitude of the torque is the magnitude of mu times the magnitude of B times the sine of the angle between mu and B. So this is maximized when this is 90 degrees. If you take B times whatever this number is. And really, that's it.
Gotcha.
Yeah, that's all the problem's asking for. Yeah, most of the torque, like I said, most of the torque problems are not mathematically difficult because of the fact that if you start putting a magnetic field that varies, it becomes a challenge.
Yeah, I don't know where my catch is with them. I don't know what is bothering me so much about them, but I blew through almost every problem on this homework except for any of the ones that had magnetic torque, and I've been stuck on them for a day and a half.
So what you want to probably try to do is find some conceptual questions to help you better understand, as opposed to doing really numerical calculations.
Right, yeah, I definitely need to go back and look through the book or rewatch the lecture or something.
So the unit 4 conceptual questions, they're online. You can start looking at those. And I have some torque questions on there.
Okay, thank you.
There's not a lot. I mean, our book doesn't get into it a lot. I mean, there's a section where it talks about the magnetic dipole moment of the electron, and so you might want to go through that. And it shows you how it's related to its angular momentum.
Right.
If you want more details, you have to actually look in an advanced book, and you probably don't want to do that.
Yeah, no, I definitely don't. This is enough for now.
Are there other questions?
Can you do number 10?
Yeah, I'm really struggling with 10.
Number 10. Let's see, what's number 10?
It's the non-conducting sphere on a sloped plane.
Okay. Did you draw a free body diagram?
Yeah, I did it with my tutor and everything. I just feel like you explaining it a little bit more would help. Because you gotta sum the forces. It's gonna have gravity and all that in it. So you really want your acceleration to be 0. Right?
Yeah.
Yeah, stay at rest.
Okay.
But I was thinking, since it's like a closed loop, there's not going to be any like net force. So like my only guess is that it's going to be related to torque.
Yeah. Hold on a second. Yeah, you want to do, it's actually easiest to do it with torque. So let's say you have, let's draw the picture. And I'm probably not going to do a good job drawing the picture. So let me draw this, and then there's loops around this thing. The loop is horizontal, right?
It's parallel to the ramp.
Oh, it's parallel to the ramp. Sorry, my bad. That makes it harder. And which way is the current flowing?
You have to find out which direction it's flowing.
Oh, okay. So you have a magnetic field that points straight up. So let me get a different color. And the magnetic field is uniform. Let me draw the normal to the surface. That okay for the normal to the surface? It's going to help me with my coordinate system. It's actually, the normal to the surface is also the normal to the loop, right? So that we know this.
Yeah.
What's this angle going to be?
Theta.
Theta. Okay, good. All right. So there's friction on this thing, right?
It doesn't say there's friction, but
because if there's no friction, it's really, I mean, how is it going to, hold on a second. It's got to stay up because of friction. You have, let me draw a free body diagram. Now I got to use a different color. Let me use red for my free body diagram. This is getting complicated. I have mg pointing straight down. I do have a normal force. And I do have friction. And mg has two components. One this way and one this way. If this is theta, this is mg cosine theta. This is mg sine of theta. That's a theta. All right. But we don't know. Well, do we know the force due to friction?
it doesn't say.
But if it doesn't roll, if we sum the forces in the y direction, in the x direction, Well, isn't F sub s mg sine of theta? Isn't that true?
Oh yeah.
Right, I don't have to know, I don't have to say anything about whether it's mu times the normal force. Students always forget that. I mean, the only time, this is static friction, so the only time the static friction is related to a normal force is at the point where it starts slipping. Okay? So that's the frictional force. So you're saying that this involves torques, right?
I thought so, since there was no net force on the ball from the current.
Yeah, because it's true that there's going to be no acceleration. This is true, but this thing can still roll, right?
Yeah.
Right, I mean, it can still roll. So there's something keeping it from rolling. And so there is a torque due to the magnetic field. There's going to be another torque. There's going to be two counteracting torques, one due to the magnetic field and one due to something else. Now that's going to depend on how we calculate the torques. Let's calculate the torques about the center of mass. Okay, let's calculate the torques about this point. We got to do that because the torque due to the magnetic moment is going to be more complicated. So the torque due to, if we choose this as the place where we calculate the torque, what torques exist?
The torque from the friction and the magnetic dipole moment.
Okay, so we have I'll write it like that. So what is the direction of the torque due to F sub s? F sub s would cause, if I pull this way on it, it would cause a rotation this way, right?
Yeah.
Okay. So F sub s is going to cause, so the torque points out of the board. All right? The torque due to the frictional force points out of the board. So we want the torque so we have B pointing this way. Which way should mu point? Mu should have a component in which direction?
The same direction as F sub s, right?
Well, mu points perpendicular to the plane of this plane, right? It's either going to point this way or that way. So you're saying it's got to have a component of mu that's parallel to F sub s. Is that what you're saying?
Yeah, so I think it would need to be downward. I'm not certain. I'm just trying to spitball.
Let's see. I'm actually having a hard time now picturing the cross product.
For this problem, would it be helpful to change the coordinate system or like rotate it?
You could. I mean, let me do this. If let's just say the normal points upward. Let's say mu points upward. Okay? So if mu points upward and you have B this way, the horizontal component of B points which way? Like that. So if you take this B, cross it with this guy, and sorry, you cross this this mu, sorry, you cross this mu with this B, what do you get? You get a torque that points out of the board. But if mu points downward, the component of B along mu points in the opposite direction. So mu has to point downward. Okay? Mu has to point downward. If I did that right. It seems like I didn't do that right. Let me see if I did the cross product correctly. Actually, no, B, I think the component of B along this points this way. Sorry. It points this way. So it points inward. So it's got to point up so that the current's got to be like this, as viewed from above. Okay. So we want the torque due to, and I'm making this long-winded, I apologize. We want the torque due to mu cross B equal to torque due to friction. This is just going to be I times A times B times N sine of theta because of the angle between these two. Now, what's the torque due to friction? Well, here's the force. This is the lever arm.
Is it R mg sine theta?
Yeah. So somehow the sine of theta is canceled out. And I ends up being R mg over A, B, and how many turns does this thing have? I'll just say, oh, 6 turns, okay.
Yeah, it's
It varies.
different for
Okay, in my case it was 6, sorry. Is that okay then? In fact, I just did part.
Yeah, that's part B, and you plug everything in for part A.
Okay.
I for some reason I just wasn't seeing it because for some reason, my tutor he did the torque by friction as mg r sine of pi minus theta.
Of pi.
Maybe he used a different angle.
He might have used a different angle then.
Okay.
But it's the same thing though, right?
Yeah, we ended up getting the same answer. The same answer as this. I was just really confused on where the the pi came from.
Yeah, it must use a different coordinate system. I don't see where that comes from, but people will set up their coordinate systems differently. Sometimes it helps others, and sometimes it doesn't.
Geometrically, sine of pi minus theta is the same as sine of theta for angles greater than or less than 180 degrees.
Yeah, so I'm trying to figure out how the coordinate system was defined in that particular case. Is this coordinate system a little bit easier for you then?
Yeah.
Okay. I generally try to do it this way. For me, it's less confusing. Some people will actually rotate everything, and that'll confuse me. But
That's what I do.
yeah, and that's fine if you do that. It's up to you. It'll be counterclockwise. When you see it from above. I actually think the harder part is getting that direction than the rest of it. Is that okay then?
Yes, thank you.
Okay. Anything else? Yeah, by the way, when you're sitting down and drawing on paper, it's much easier to draw them than when you're doing it on the board. I don't know. That takes me longer if I have to figure out directions. So yeah, the direction will be counterclockwise from viewing from above.
I actually have a question on the exam.
Okay.
Or for this upcoming exam. So the date that we're going to be doing it on, was it May 4th or something like that?
Yeah, it's a Tuesday, right? Let me check.
Yeah, May 4th. That's set in stone, like it would not get pushed back to the 6th.
Yeah, I part of it is because the next exam comes up very quick, so I really don't want to change that.
Okay, I was just making sure, just because I have a flight on that Thursday, and I didn't want to have to reschedule a flight. So
yeah, I'm not going to change it.
okay.
Yeah, I'm going to say so. You're flying back at night. Is that what you're saying?
No, I'm leaving that Thursday.
Yeah, I don't change. We're actually time-wise we're okay. So next week in lab, if I look at the schedule, if next week in lab it actually says discussion of magnetic field, so I can use whatever I can use that day to catch up. And in fact, one of the things I haven't done yet, I was going to create a video on something called the displacement current. This has to do with the correction to Ampere's law. And I think what I might do is use the lecture next Thursday to talk about that topic. Actually,
Okay.
no, that's not right. That's too far ahead, sorry. No, I'm going to have to make the video, sorry. I'm looking at the schedule. We're actually a little bit ahead right now. We'll see. I might actually use a lecture just to talk about it. Okay. But right now we're pretty much on time. I mean, we're pretty much on pace. And maybe a little bit ahead. But
And then I'm also looking at due dates for the homeworks after that. So we have that exam on May 4th. And then it says the next homework is due the 9th, which would be a Sunday.
yeah, so I'm going to be starting the next chapter. I'm going to start the next chapter right away. In fact, I'm scheduled to start the next chapter, the new unit on the 28th. And so I'll get half the chapter done in that lecture, maybe more.
Okay.
Okay, and then the second lecture will be on May 6th.
The 6th.
Yeah, so I'll finish the chapter.
All right.
Okay. It's not a long chapter, and maybe I might go a little bit longer. I don't know. We'll see. It just depends on where I'm at. Sometimes some of the discussions get a little bit longer on that topic. So we'll see where we're at. But right now we're in good shape, and I'm not going to change the date on our exam. It causes all kind of issues for students. And then of course the last one's kind of dead set on too because it's the last day.
Yeah.
Okay. Other questions? And the display is getting blurry, isn't it? Oh, this is just me. It looks like a display.
It looks the same as it was.
Oh, that's not good then. Yeah, this file is getting kind of big, so I'm not sure if that's part of the issue. Because I'm recording on a separate camera, and then I'm using what you're seeing is a virtual camera. What you see on Zoom is a virtual camera, not. It's a camera that's run through another piece of software. So I'm using a lot of resources. So sometimes when I use a lot of resources, it just looks a little bit blurry. I don't know. If you guys don't have any more questions, I guess I'm done, and you folks have a good weekend.
Thank you.
All right, thank you.
All right.